Okay, so on to problem 3. So this is on ADC and DAC. So the part A is asking, assume that the registers have been properly initialized, write C code to take a value from the ADC channel 0 and use it as input to DAC. So this is really just looking for, do you understand how ADC and DAC work and generally what the registers look like? So we want ADC channel 0 here, which if we look at the general register description, we can see that we have the control register, the global data register, which we could use for this if we wanted to, and the interrupt enable register, and then data registers for each channel. So there are 8 channels total. Here we're asked to get the value from AD channel 0, so this is probably the best thing to use here. So we want to take something from AD-DR0, and if we look that up, we can find, or maybe we can't, AD0 DR0 is I think what it actually gets listed as here. Yeah, there it is in the right column. So this gives us the address that we need to use for that pointer, 403410. That's where we'd find that. And then if we look up what it looks like, we can see that it has 4 reserved bits and then the result from bits 4 through 15. So if I'm trying to get the value from the ADC, that result is what I'm asking for, is that 12-bit value that's coming out of there. So I can take that, dereference the pointer so I can get the actual value from memory, and if I shift it over by 4, that puts it from the 4th through 15th bits into the 0 through 11th bits, and then I'm going to AND it bitwise with FFF, so that is 12 bits of 1s. That's basically going to get rid of anything that was in these top bits, right? So if there was a done bit, if there was an overrun bit, or if anything happened to be in these reserve bits here, that AND is going to get rid of those bits. So that's my 12-bit value from the ADC that I got. Now I want to put that value into the DAC. So let's look at the DAC. And this is pretty simple here. We have the DAC converter register. That's where we put a value that's going to come out of the speaker or otherwise come out of the DAC pin. So that's organized as follows, which is it has 6 bits that are reserved, 10 bits for the value, and then a bit for bias, which we can ignore. We're not using this, and then more reserved bits. So what we have to do here is end up putting the value we got from the ADC into this value here, which is only 10 bits, and we got something that was 12 bits. So what we're going to do then is normalize the value that we took from the ADC to be within the range of the DAC. So the ADC was 12 bits. If we do 2 to the 12th, that is 4096, so that's the max value coming out of the ADC. And the DAC is 10 bits, so that's 1024. That's the max value we can put into the DAC. It's actually 1023 and 4095, but we can normalize by the sort of total number of values that are there. So we want to divide the value by 4096. That gives us a number between 0 and 1, which is essentially like the scale, how big of a value this was in terms of the full size of the ADC. Then we multiply by 1024 to put it within the range of the integers that the DAC can represent. And that leaves us with something between 0 and 1023. And if we shift that over by 6, that puts it into the correct position within the DAC. And of course, I took the address of the DACR to put into that pointer there and put that in as 4008 C000. So that's just, again, kind of understanding, is really just looking for some understanding of the sizes of the ADC and the DAC, that the ADC is 12 bits, the DAC is 10 bits, and being able to write some basic C code on them. So the next question here is, assuming that the P clock is 100 megahertz, ADCR is equal to the hex given there, and that the ADC takes a sample every 65 cycles. So really we're looking at the ADCR register here, so I'll pull that up. So this is the AD control register, AD0CR. And we're looking at this in hex to see what's happening here. So first it asks what channel is being converted. So if we look at the description, we can see that cell, the bottom 8 bits, are the channels that are to be sampled and converted. For AD0, bit 0 selects pin 80.0.0, bit 7 selects pin 80.0.7. So here we're looking at this to see what are these last 8 bits, which is 2 hex digits, which channel is being selected. And since we write that out in binary as 0000000001, that's bit 0, 1, 2, 3, 4, 5, 6, 7. So bit 0 is set to 1, which means it's channel 0 being converted. And then what is the sample frequency? So the sample frequency is how often we take a sample on the ADC. So we have to factor in the clock speed and how fast, if there's any clock div, and then we have to factor in the fact that it takes 65 cycles at that rate, so at that clock frequency. It still takes 65 cycles to do this process of converting from the analog voltage to the digital value, because it does this sort of successive approximation where it kind of guesses a value, checks to see how close it is, guesses another value, checks to see how close it is, etc. So we're going to do the clock speed, which is in cycles, divided by... okay, so it looks like this is a bug in the solution here. We should be calculating the number of cycles per second on the CPU divided by the clock div, which is clearly these 8 bits here are supposed to be the clock div. We add 1 to it as shown in the manual here, so this is these bits plus 1, so normally these bits are 0. That means the clock div is just dividing by 1. So we don't end up with the divide by 0, but that ends up giving us 10 divided by 10, which should be 10 megahertz. And then at that speed, it takes 65 cycles to do one conversion. So I think this should be halved for about 76.92. I think maybe I jumped ahead on this step and added in the Nyquist theorem twice, basically. So for this one, it should just be, again, clock speed divided by the clock div divided by the number of cycles that it takes to process a single sample. That'll be the kilohertz frequency that we sample at. And then this last problem, part D, we're looking for maximum frequency to avoid aliasing. So if you see the word aliasing, you should immediately think Nyquist theorem, which is that we can sample, we must sample at a rate at least twice the maximum wave speed. And so that allows us to basically ensure that we have a sample in the up part of the sine wave and a sample in the down part of the sine wave. So it allows us to know like what the general shape of that wave was supposed to be, where it was supposed to be at that point. So here we're just basically dividing. In this case, we're going backwards. So we want to know, given that I can sample at, let's say we'll use the error carried forward here of 153.85 kilohertz. That's my sample frequency. The maximum thing that I can sample is half of that. And so if I divide, I need to be at less than 76.92 kilohertz, according to the Nyquist theorem. So that's it for part 3.